This section is about using and creating exponential models to solve problems. Of course, it's much easier if you're given the equation. You just need to find the information that's missing. Our example, we have a model or an equation to determine the number of cell phone subscribers based on time or years after 2000. Our goal is to determine when the number of cell phone subscribers will reach 90 million. Now our model is given to us in thousands, and we're asked to find when it reaches 90 million. So we need to convert the 90 million to thousands first by dividing by 1,000. So that would be 90,000, setting it equal to that equation. And then we'll solve our equation for t. First step, dividing both sides by 5,535. We get about 16.260 rounded to the nearest thousandth. To solve an exponential, when the variable is an exponent, we're going to take the log of both sides. You can use log of any base. I'm choosing natural log. You could use common log. You could convert and use log base 1.413. All three of those methods will work. Using the power rule on the right-hand side, I'm going to pull that exponent down as a coefficient and divide both sides by natural log of 1.413. And our answer rounded to the nearest year is 8, which means in the year 2008, there should be about 90 million cell phone subscribers. The next two examples we're going to look at, we need to create the exponential model in order to use it to answer questions. What we're given here are two different ordered pairs. Time is always your x value if that's an option. I'm going to call year 0 1990. So our first year, or 1 year after 1990, we had 28,500 cases. 6 years after 1990, we had 22,840 cases. Remember our equation y equals ab to the x. I'm going to use the second ordered pair first. So I have 22,840 equals, we don't know the initial amount, we don't know the rate of growth or decay, but we do know the time was 6. We're going to do the same thing for that first ordered pair. And in this case, it was to the first power. What we have is a system of equations. If you remember how to solve systems from algebra, you either added them together or you did substitution. In this case, because the variables are being multiplied, we are going to divide our equations. 22,840 divided by 28,500 is about 0.801. A divided by A cancels. B to the 6th divided by B to the 1st gives me B to the 5th. This is why I used the second ordered pair first, because the x value was larger, and when you divide, you want a positive exponent left. Then we'll take the 5th root of both sides. We get about 0.957 for our b value. Our b value gives us the rate of growth or decay. As we could tell, the number of TB cases was going down, so we have a rate of decay. We can use that to solve for a. I'm going to use my first ordered pair because the power on my b was 1, so it'll be easier to solve for a. Dividing both sides by 0.957, and remembering that our a value means initial amount of cases of tuberculosis. You can't have a partial case of tuberculosis. A person can't have half tuberculosis. They either have it or they don't. So we're going to round this to the nearest whole number. And we get 29,781 rounded to the nearest whole number. Using our A and B value, we're going to write our model now. Y equals our initial amount, 29,781, times that rate of decay, in this case 0.957, to the t power, t being years after 1990, based on the way we set up our model. We'll use that equation we just wrote to predict the number of cases in 2000, which is 10 years after 1990. So we've got 29,781 times 0.957 to the 10th power, which gives us approximately 19,189 cases, rounded to the nearest whole number again. And the last question is asking us to determine how accurate the model was. The actual number of cases wasn't off by a whole ton, but here's how we find the percent of error. You take the difference, you simply take the larger number minus the smaller number. Order doesn't matter. If the actual was larger, then you would start with the actual. In our case, the predicted was larger, so we started with the predicted. And then you divide by the actual. And that will give us our percent of error for our model. We get about 0.007, or a 0.7% rate of error, which is pretty darn good. Again, we've got a rate of change over time. We've got these two ordered pairs. So I'm going to call 1960 year 0, and our land was worth 30,000. And in 2000, which is 40 years after 1960, our house was worth $212,000. Setting up that y equals ab to the x, using that second ordered pair first, we had a value of 212,000 equals, and since we called 1960 year 0, we do have our initial amount. The house was first worth $30,000. What we don't know is the rate of growth, but it took 40 years to get to that value. Dividing both sides by 30,000, we get 7.067 is approximately b to the 40th power. So we'll take the 40th root of both sides to get our rate of growth, which is 1.050. And when we write our model, we will just round to the nearest hundredth. Knowing the initial amount already, our model is y equals 30,000 times 1.05. We had a 5% rate of growth in the value of our house each year. Using that model to predict when the value of our house will be $350,000, we substitute that in for the value after time. Dividing both sides by 30,000, we get 11.667. Taking the log of both sides, you can use common log, you can use natural log, or again, you can convert to any base you want to. This time I'll use common log. On the right-hand side, we're going to use our power rule and pull that power down as a coefficient. And then we can divide both sides by the log of 1.05. Rounding to the nearest year, it will take about 50 years for the value of the house to reach $350,000, which would be the year 2010, 50 years after 1960. As a reminder, we had 2 additional questions on this one. Does our answer seem reasonable? At first, sure. House prices continue to increase. However, if you think about the economy in the year 2007, 2008, we hit a pretty serious recession and house prices plummeted. So the fact that this is predicting a 5% growth throughout the recession is not reasonable. And here's your U-try question.